Let's do number 5. I skipped number 4 because that's a question for an RL circuit, and we didn't cover RL circuits this session. So number 5 is asking for the self-inductance of a solenoid. So this is one where you are changing one variable and see what happens. So the equation for the inductance of your solenoid is mu naught n squared, number of loops times the area divided by the length of that solenoid. And it says that we are just tripling the area, so all we're changing is we're making the area 3 times as big. So all that does is it multiplies the whole inductance by a factor of 3, because you can just factor that 3 out. So that's why the answer is 3 here. For the next one, we have a flat coil, consists of 20 turns, and it's positioned perpendicularly to a field that is changing. So what's going to be the induced current? So first we have to make sure that there is an induced current, that there is actually a flux changing through the loop, that the loop is positioned so that the field lines are actually going through it. So the flat coil is positioned perpendicularly to the field. So if you could visualize it as the coil is horizontal and that field is perpendicular to that coil. So that means that the magnetic field lines are indeed going through the loop, and then that field is changing, so you definitely will have a changing flux and an induced EMF and current. So to find it, we're going to use Faraday's law. Induced EMF is negative n change in flux per time. And then we figure out which variable of the flux is changing, because flux is defined as AB cosine theta, and it's the field that is changing. So we can take the area and the cosine theta out of it and just look at the change in the field divided by the change in time. So I just took A cosine theta out of the change here because they're not changing. And then we have to figure out our givens. So 20 turns is N. The area is 50 centimeters squared, but I will write that on the side because we do need to convert it to meters squared. And that's going to end up being 50 times 10 to the negative 4 meters squared. Remember that in your conversion from centimeters squared to meters squared, that you don't have 100 centimeters squared in a meter squared, you have 100 squared centimeters squared. So when you do that conversion, you get that factor of 10 to the 4. So this is the area, and then the change in the field, it goes from 2 to 6, so final minus initial is 6 minus 2, which is 4 Teslas. So we have N, A, B, we need to change in time. This is delta T here is the 2 seconds. And we just need theta. So the way we pictured it, we know that theta is defined as the angle between the normal to the plane. This is the normal to the plane. The angle between the normal and the field. That angle is 0. Which makes sense because you're going to have maximum flux in this orientation. Maximum flux means cosine of theta has to equal 1. That's how you get the maximum flux here. So theta has to be 0. So now we can plug in our NA delta B divided by T, and I got 0.2 volts. And now we can find the current because we have the resistance. So the current is the induced EMF over R, this is Ohm's law, 0.2 divided by 0.4, and you're going to get 0.5 amps. but 0.5 amps is equal to 500 milliamps. Let's do one more. A loop of area 0.25 meters squared is in a uniform magnetic field. The flux through the loop is this value. What angle does the normal to the plane make with the direction of the magnetic field? So it gives you the flux, and the flux is equal to AB cosine theta. So solve for theta, because you're given, this is the flux right here. You're given the area right here, 0.25, and you're given the field right here, 0.02 Teslas. So when you solve for theta, you're going to get the inverse cosine of the flux divided by AB. And you're going to get 40 when you do that. And that ends up being the answer. But always pay attention to the angle, because the way that the flux is defined, if you have a loop and you have a field going at some angle, you have to draw that normal to the loop. And this is theta. This is how the theta in this equation is defined, from the normal to the loop to the magnetic field. And that's the theta that we just solved for, and that's also the one that it asked for. It said the normal to the plane with the field. Now, if it had asked for what angle does the plane of the loop make with the field, then it would be asking for the 50 degrees. But it actually asked for theta, so we're good to go.